Thank you so much. Really happy to see the turnout that we have today. Thank you so much for Phil and the team to organize. It's our very first event actually here in New York City since we moved from the UK. We were founded in Cambridge, based in London, and it's our first time we're presenting TypeDB to the New York City community, so we're really excited for that. So to dive in real quick, so as Angela kindly introduced, I'm Heiko, founder and CEO of TypeDB. We've been working TypeDB in the current form that it is today, that we know it today, for the past 5 years. But the idea originated 10 years ago when I was working as an optimization scheduling algorithm designer. So typical routing problem, scheduling problem, optimization for graph planners, and typical NP-hard planning systems. And so we always work with like a lot of data sources, as you can imagine, like literally 50 to 100 data sources, where each of them have like 5 to 10 tables each. And so you're modeling really, really complex schemas. You're writing joins in queries that basically span across multiple tables. And as you can imagine, when you get to like 5, 10, 15 joins and the queries, it can return in an hour. It could not return. You don't know. You'll find out later in an hour if it doesn't return or not. And debugging it takes a long time. And if it returns null, does it mean your query is wrong, or does that mean there is no answer, right? And this was a huge pain. And we realized basically, like at that point, like why do queries at the database basically get unwieldy really, really quickly? And the first realization is that we don't have the ability to model complex problems at the database level in the way that we do in programming, right? We solve this problem in programming with abstractions, with the notion of interfaces, classes, generics, functions, variables. But we don't have the ability to work with the same kind of abstractions in databases. And you realize to do that, we actually need to introduce better type systems at the database level. And that's going to be really hard to work against relational algebra. And so you need to have a different kind of algebra that allows you to introduce better type systems at the database level. So that was the original inception of the idea. There is a paper, the type theoretic algebra behind TypeDB and TypeQL, that's published in ACM last year, that you can find on our website. We're not going to get into that today to bore everyone out. If you're interested, some have asked, you can find that on our website. And we're also not going to look at the entire breadth of what it means to look at to have the power of abstractions from programming languages in databases today, but we're going to look at specifically the effect of having type systems in a database where you can validate your queries and you can actually use the information in the type system to optimize the queries further, so that when the queries get more complicated, it actually runs faster, because that's what type system is supposed to do for us in programming languages, and there's no reason why we shouldn't be able to leverage that in query languages. And so today, Joshua, our head of engineering, who's led the development of TypeDB 3.0 in Rust, will share this glimpse, this dimension of TypeDB that we're very excited to share with you today. So, all right, Joshua, over to you.
Thank you.
Yeah.
Hi, everybody. I'm Joshua. I'm the head of engineering at TypeDB. I've been working with Heiko for 7 years almost now. So we have a long history working on this project and the product that we have a good passion for. So as Heiko alluded to, we're going to be talking about a very specific slice of the system. There are many layers to it. There's much more to it. There's the engineering, there's the theory, there's the language design. But given this is a systems talk, we're going to talk about languagey, compilery stuff and how it relates to databases. Thank you for our host, and thank you, Heiko, for the intro. So why do we do this? Well, we started this project because SQL has some problems in it, right? There's a bunch of things you can do in SQL, and there's some things you can't do in SQL. But there are some things that you can accidentally do in SQL that are stupid. Particularly some of these things that I've outlined. So you can join any two tables you want to, as long as the data types match up. You can forget to add foreign key constraints. So if you forget that and you delete a row in a table that's being referenced somewhere else, system won't warn you. That's a problem. And it's designed a while back and has this idea of nulls, which I believe Tony Hoare has described as the billion-dollar mistake, which he regrets. And we can do better than that as well. And fundamentally, what we're talking about here is a lack of structure in a system, a lack of expressivity in the type system that powers common databases. And why is that? Well, and where we've really seen the development of databases over the last 40, 50, 60, 40, 50 years is that they've initially started to abstract away the hardware. And then they started abstracting away the file system. And from there, we had relational. And that was the whole CODS, relational algebra. But where do we go from there? We started getting more scaling problems in databases rather than expressivity problems. So the data was just growing in volume. It wasn't really growing in complexity. So we get NoSQL as a movement, really, as a philosophy, which spawned key value stores, which spawned column-oriented storages, which spawned document-oriented databases, which really, like MongoDB, came around when the internet came around and scaled all the data that was being produced and accessed. And a slightly different dimension is we have graph databases as a common pattern, and like timescale and other types of databases, it's really made to express more niche patterns or certain properties that you want to exploit of your data. So the dimension of growth of database systems over the last decades is not in the direction of solving some of those fundamental problems within the system that we're started with, but really just like enabling scale and enabling specific patterns. And we think there's other dimensions we can look in. Where can we look for inspiration, right? So Heiko's alluded to it in programming language land. But if we look at programming language land, you have this wide, wild variety of programming languages you can choose from to suit your problem. So if you are building a performance-sensitive, safety-critical application, you're not going to use a very weakly typed system that is going to allow errors to sneak in if you can eliminate them just by having a static type checker at compile time. So you might choose something like Scala or Rust, which would be up there in the top right, because it gives you very strong guarantees for safety inherent to the system without having to write more tests and do manual inspection. But let's say if you're just scripting something up and you want to move fast, because some of the cost of those strongly typed systems they're a little harder to use sometimes. You have to learn a little more. So you might just write Python to hack out a script when you don't need it to be performance or safety critical. But you have a choice, right? You have a choice. And in database land, we don't have a choice. So you don't have a choice when you are building something that's safety critical to invest a little more upfront to gain more safety guarantees and to have more expressivity to express your complex problems. So that's kind of an inspiration we could go in. The two classical axes of describing programming languages in terms of type systems. This is the two axes. This is not my image. I've borrowed this from someone. It's all over the internet. I couldn't find the original source. But you have dynamic and statically typed systems. So a dynamically typed system allows you to mutate the types of things kind of much more freely. You can turn an int to a string, and there's some built-in way to do that. And that may or may not be safe and what you want. A static type system has very specific rules about what you're allowed to do. And those are checked ahead of time. Sorry, I might have flipped those. Yeah, but anyway, strong type systems are things where everything is really well specified. So something like C and C++ is generally considered weakly specified because you can always circumvent the type system by going to a raw pointer and manipulating the data and the memory directly. So you can circumvent the type system. But a stronger type system like Java, you really have to work very hard to do that. So these are the axes of type systems generally. And so, you know, it's a little counterintuitive, I think, actually, to think that to build a more strongly, a more expressive system in a way that's safe, you impose more rules and more specialized first-class constructs. So it's almost like you're taking away general capabilities and assigning to the very specific classes and assigning rules of how all these things interact, and it seems much more complicated. Like in Python, you can just add a string, or in JavaScript, you can just add a string to a number and it'll work somehow. But if you establish very strict rules, the system can do more for you, right? So let's consider what that could be in SQL. Let's say, to think about the problems on the first slide, the second slide, SQL doesn't have the idea of a relationship. It's just another table with columns in it. It doesn't have some kind of type to indicate foreign key constraints. There's this little constraint you can add, but it's not really a first-class citizen, and it's easy to leave out. It's not inherent to the language. And missing values, the type system behind nulls is you have your space of values you can have, and you tag on plus null. Right? You can have all the values in any data type plus null. That's a valid value in any space. But modern systems will often have the idea of an option type, which feels very similar, but you can do very different validation and constraints and operations over an option of a value when you have that over a value that could be a value plus null as a value. So fundamentally, I think the argument is that SQL just doesn't have the structure and the constraints and the rules and the first-class citizens to do the validation and solve the problems we would like to solve. Right, so let's imagine we had a database with a strong type system built in. What would that look like? So what I've got here is actually a snippet of TypeQL, which is TypeDB's query language. And this is the definition of a user's type system, which happens to double as the schema. But the type system in our world has first-class constructs and things you can do between them. So there's the idea of a first-class relation. Unlike in SQL, where a join table is just a table, we have the idea of a relation, which you declare. You declare, I have a relation, team membership, which has what we call two roles, member and team. This is a first-class type. It's different from an entity type. So an entity type is yet another category of types, but it's a type, and you can declare a new type in that space. I'm going to define as a user the employee entity type. I'm going to give it some capabilities. So an employee can own a name, which itself is a type. Happens to be at the bottom the attribute type, and an attribute holds a value. Right? So we have, in our world, we have relation, entity, relation, attribute. Entity relation models are very close to where we are. And you can do things between them. So a relation can have roles, and then your entities, or even other relations, side note, can play roles in those relations. So we have an entity, employee, playing, team membership member. This is equivalent to a foreign key constraint in SQL, but it's a type, right? So we're saying that you're basically defining in programming language equivalency, this would be a set of traits. You would have team membership member as a trait, and you're implementing that trait on employee. This is a type theoretic way of thinking of how data is connected. Further, we can start to give the system more information. So we can say an employee is allowed to have a name, but exactly one. Right? An employee must have a name. It's a very sensible real-world constraint. Everyone you employ must have a name. Maybe you have an email, some other things as well. It's a simple model, but let's say they have a name. But a team may have a name. The team can have 0 or 1 names. We could even relax this to have 0 to infinity names. But for this world, we're going to have 0 or 1 name. And now the system knows. It knows that the name an employee owns is a non-optional type, and the name a team owns is an optional type. Again, these are not things you can distinguish in SQL. At least you can put a not null constraint, but it's not part of the type system. All right. Now, we have defined in the previous slide a type system for the user. It's a specific, specialized type system for you. What can we do with it? Well, we can put some data into it, and then we can look data up. How do we do that? It's basically a pattern match. Rather than writing select something from something where something, we roll all of that into one clause, which you call a match clause. And you use the same language of your types that you use to define your schema, your type system, to look up data. And it's really very readable as natural English. You're looking for an employee, an instance of a type that is the employee type, right? Employee is a employee. $employee is an employee. This is a typing judgment, a term in a type. And you're saying this particular employee that must have been created at some point has the name Alice. You're looking for some other substitution for the team variable from the team type, its space of terms, which has the name team A. And you're additionally looking for a team membership, which is a relation type, which links these two through particular roles. Right? So this is a query that uses the definitions you've provided the system in your type system to look up data. And the cool thing is now that because the system has well-defined semantics for what each of these little pieces means, it understands how these things are connected to each other in the schema, we can start to do fun stuff with that. This is for the theory people, but we'll forget about that for now. Right, so we have a well-defined type system. We have a well-defined, it's useful. I mean, we think it's useful. We have clients that think it's useful. It's general. What can we do that maybe we couldn't do before, right? So one cool thing that falls out of this is you can actually meta-program your queries. You can query the schema as if it's data, because it's just a constraint satisfaction language at this point, and say, I want an entity type that has a name. And then I want to look up all the instances of that entity type. This would be like saying, in relational, first variabilize the tables and look at the tables that have a particular column name and then union all the columns. You can't really do that. It's not part of the language in a nice way, you know? This is, you can make this as composed, as complex as you want, and it'll all boil down naturally to look at the types, look at what substitutions for types there are in the instances, and return some answers. Another thing we can do is a little more than syntactic validation or simple constraint checking. We can do semantic validation. So if I ask the database, find me an employee that's participating in a team membership as a team, made a typo, used the wrong role, system in SQL, if you were to join these two columns that happen to have the same type, you might just get no answers because there are no employees that are team that are part of the team column. But here we can say this is a semantic error. You've actually written something that's illegal in the type system you've defined. I kind of think of this as a compile time check in a statically typed language. So if you write some nonsense, you put a string into a list of integers, the system can reject you. It's not just going to do an accidental cast and make it go in, you know. So this is really getting at the root of it, which is it's powered by type inference. And to allude to the optimization element that Heikel mentioned and is in the title, you can actually do more with this. So the type inference engine, which I'm going to touch on briefly after this, is going to basically assign possibility spaces to every variable. So we're going to say that this member variable down here is going to be something that is a member in a team membership. And we can go and look at the schema, and we can do a graph, like a pass through the schema and do some elimination and reconciliation, and we can find out that the only possible type that can be in member is employees instances, not teams, because teams can't be members. They can only be teams in this relation. So the more types you have in your query, the more likely it is that the automatic type inference can prune the search space and reduce the number of spaces to search, which I think is pretty cool. And we haven't really fully exploited yet, but we are always looking at that. So what is the core of this, right? So now we're a little more into compiler land. Our database is structured quite a lot like a compiler. So we have a language, we have an intermediate representation, we have some static optimizers, we have a type inference pass, which annotates the whole thing. And then we go into more traditional database land of like costed dynamic planning and then the execution over the storage layer. But the bit in the middle is really a compiler. And a big part of that is type inference. So when we do type inference, we basically form a graph out of the query with nodes. So we take every variable you've written, whether they're explicitly written or hidden, and we say you've written that you're looking for an employee variable. And you've said it's an employee. So we're going to make this kind of graph connection saying the employee is a type, an instance of the type employee. And I've made an internal variable there on the right. This $0 is a team membership representing something from the relation space of team memberships. And what we're looking for is to validate and make sure that the team membership instance is allowed to link the employee via a team membership team role, right? So what's the system going to do? And this is an extremely simple version, but it's good for a presentation. This side is fine. This side is totally fine. The schema says, great, yeah, team membership type, which is the type we can derive from that is a constraint on the right, is allowed to relate to a role team. Schema says, great, you can do that. But over here, you've derived that the employee is of type employee because of the is a constraint, but this is not allowed in the schema to play the role team membership team, right? This graph can get very large. We've had queries with hundreds of variables in them, and then you get very complicated propagation of these constraints mean that this must be this, which then reduces this search space, which reduces these set of types, and you propagate it back and forth till you find a fixed point. And then you might find out, oh, this one variable is not satisfiable. And that means your whole query is not satisfiable at this point. And we can reject the query. Semantically, this is an error. Your model does not permit employees to be teams. Makes sense. I've pulled a slide here out of a more theoretical talk. I've got the QR code, and it's on YouTube by our colleague Christoph, who wrote the paper that Heikel was talking about. But the formulation of all of this is in dependent type theory. So we have independent types in our system, and we have dependent types. And it essentially is this nice tabulation of everything we can do in the system falls under a matrix of independent, dependent, and it's either an object type, an entity or a relation, or an attribute type. So we get this nice, clear diagram. There's a lot more theory to go into if you're interested. It's very fun. It goes into a lot of the motivation and stuff. Highly recommend watching it, but I think it's a little out of scope. Primarily, the fun thing to notice here is that we have a new model. So we call it the PERA model. I've put polymorphic in brackets because we haven't even got into the polymorphism, but it's fundamentally an entity relation attribute model. We think it's very intuitive to people. Entity relation diagrams are what you by default normally draw when computer scientists get to a whiteboard and you start being like, I need to do this, and we end up with boxes and arrows, right? That's very natural. So when you're modeling a database, you do that, and you basically take that diagram and you turn it into text, and that's your schema in TypeDB. It's a very simple conversion. There's no normalization and denormalization. Our users' first models are normally very intuitive, easy to read, and English.
Which is based on the ER model by 10.
It's based on the ER model, which is also a section in the theory. So what do we have? The TypeQL model is the PERA model. It has a database schema defined as types that are defined by you as the user. We have imposed our own structures. So rather than saying there's just types, we have, like in languages, you have just objects, right? Everything is a subtype of object in Java and in Python. But here we have three roots. We have the category of entities, relations, and attributes, and they can each do certain things and relate to each other in certain ways as the connections. And we can also define how frequently and to what strictness they have to relate to each other. So in SQL, if you have a key constraint, we have a key constraint saying a person must have a key email. That's a kind of cardinality and the uniqueness constraint put together. How do you use that to do data? Well, you just, like in an object-oriented programming language, you take your type and you instantiate it. So when you say, I don't have an insert here, but you say insert x is an employee, that creates a new instance in the database, which is data. So your data is not represented in rows or documents. It's conceptually instances that you just directly say, database, instantiate these two things and connect them with an instance of a relation. Boom, you think in instances and types, not rows and documents and vertices and edges. Right, so polymorphism, haven't touched on it a little bit. There was a hint at it earlier. The meta programming is a kind of polymorphism. You're doing a structural polymorphism kind of where you say anything that conforms to this kind of structure can be fed into the next part of the query. but there's other forms of polymorphism we do. I would say watch the YouTube video. Right, so at this point, we've got a new foundational layer for database schemas based on a new mathematical foundation, not relational algebra, but dependent type theory. And in our experience, it leads to a really general, expressive, and easy to use model that is also strongly typed. So we can do all the fun validation that programming languages do and some of the optimization they do in the database layer, which is really cool. As a result, the system has a lot more knowledge about what you're doing, if it's correct, the data integrity, you can put more constraints in place. There's like every time we sit down for a talk about what else we can add to the language, it's like 2 years of work. So the potential to keep developing the language because the foundation is so sound and rigorous and expressive is like we can imagine building so much more on top of this. I say general also, I want to flag there. It's general. So you can actually express relational algebra and practically tables super easy in TypeQL. Anything that's just a join table is just a relation. Anything that's a simple table with values in it is just an entity with attribute ownerships. So you can express all of relational algebra in TypeDB very easily. Same with graph. You just make an entity that's a vertex and an edge that's a relation and make it two ends of it. That's a binary edge. And then you can do that. You can do hypergraph modeling easily. A relation is just a multi-way edge between vertices, which are entities. So property graphs and relational SQL databases are super easily absorbed into our model. So we say it's general. There is a way to convert document into TypeQL as well, but it's a little more involved. So the mapping isn't so like that, but it is possible as well. And I think Christoph has it in the paper that he published. So it is provably general, general enough to encompass pretty much all the general purpose transactional database paradigms that exist right now. So we think that is proof that like it's useful. You know, everyone else using that, and you can do all of that in here. So it's at least as good in terms of expressivity. Right. So coming back to why we did this. So you can validate queries, alluding to what Heikel was saying about his complex optimization queries to integrate data sources. The database can now tell you if your query is correct because you know the difference between no answers, meaning an error, and no answers, meaning there are no answers. The system will now never let you write a query that's impossible. You can't join two things that are wrong. There's no more nulls, so there's just absence of things in our system. You just don't have a name. You don't have to insert a null. It's like employee, if the team doesn't have a name, there's no name. You don't have a null. It's easy. And you can just do an optional lookup in the query language to make that available. Haven't also touched on this, but based on this, we can build abstractions. So not only do we have entity, relation, attributes, and actually these role types, we can do subtyping as well. So when you create a team type, you might make like an internal team and an external team subtype, and then you can basically build towers of types that automatically get collapsed during type inference, and the system understands if you're looking for a team, that means it's a team, an internal team, or an external team. So you have the abstraction of inheritance and subtyping and another form of polymorphism. We also have functions, because you've seen variables and you've seen constraints and types, and now we can build functions easily, and functions return these rows that you can operate on. What else do we get? So in the early diagram of programming languages, you had this axis, right? And there's a huge smattering of different programming languages you can use. You've got a certain need that you need to meet, and you get to pick what you want to address that need. And what we're presenting is basically yet another choice. In SQL, you don't have much choice because there's just the SQL standard. You can go to document, which throws out the schema. You can go to property graph, which throws out the schema. And now we're trying to evolve a different direction as well. If you're safety critical, you can use a system that helps you with the safety of your system rather than allows you to shoot yourself in the foot. A little bit like Rust also, right? Because we're aficionados of Rust because we wrote the new thing in Rust. But it is very aligned in philosophy. It's like you pay a bit more upfront cost, you think about your model, you do that before you write too much. There's not too many ways to do it correctly, but when it's correct, you get better models. It's more composable, it's more maintainable, you get fewer errors, the system will help you. And yeah, we think that because the abstractions we've built and the way it's expressed in pretty natural English with variables and types and functions and polymorphism and subtyping and all of that, it's very close to familiar programming languages. So if you've used a set of programming languages that includes a object-oriented programming language and something with streams in it, because that's how our queries are actually mentally modeled, you basically can understand everything that's going on in the system. And lastly, the optimization thing. We can do this type pruning, we can detect dead code, we can do query rewriting, all of that stuff based on types, and improve the performance of the queries the more type information you give it, which is super cool. So, we've heard this a couple times. This sounds too good to be true. Yeah. What's the catch? So what we find is that, practically speaking, because it's a very easy to use language and system, and we try to make it accessible, people write ad hoc queries all the time. And it's so easy to do. It's just, now I'm interested in adding another join, or another hop, and then like this, what if this person has this value, and then I want to add this other constraint over here, and like imagine forgetting an index somewhere in SQL, it'd be horrible. So we basically index everything that makes sense to be indexed, and we can do that in a sensible way because we have a type system, but that costs a disk. And we're generally okay with that. Our cost is that developer time is the most expensive, and then it's CPU time, and then it's memory, and then it's disk. Yeah. So we will trade disk time, disk space, and cost to get all of the benefits of what we're seeing. The other question we get frequently is performance. So we're in the early days of benchmarking. We finished our 3.0 Rust rewrite, which was with the aim of performance. And we're just starting the optimization journey, but what we're seeing is that we scale pretty well. We're still in the small scale. We fall behind Neo4j, who we're comparing to, because that seems to be where most of our users are coming from right now, because it feels kind of graphy. But we're starting to see that our model and the way we built it and the way we encode it into storage and disk like that scales better than the way they've done it. And it suits the regime we are targeting, which is beyond memory scale. And we're pretty confident we can, if we push this whole thing up 20%, which we know there's lots of overhead for us to remove still, that will be meeting more around where you cross the memory threshold, which is a good goal for us to be at in this point on the journey. And where are we going? So obviously performance is still part of what we're improving. For instance, our queries are not parallelized at all right now. Every operation runs single-threaded, and you block on disk every time you get something, and then you go to the next operation. The query plans are linear. There's lots of room for doing things in parallel. So there's a big multiplier there. What we're trying to get to is, let's say, a common deployment of, let's say, 100 gigabytes of data, and you have 10 gigs of RAM. That's a pretty common ratio, 10%, 10% we see at scale. So if it's a terabyte, people have 50 to 100 gigs of RAM. That's pretty common. A lot of relational databases will not perform well if you have less than that, because they have to store their indexes. So it's a pretty good ratio. We're confident we're already beating Neo4j there, but we want to keep pushing that number to be comfortable when your memory is 10% of your data. There's a lot of room for, as I alluded to, every time we think about the language, we have years of ideas, but the close-term ones are there's no native support of ordering yet, so if you want to store a list, it's not possible. You have to manually insert a bunch of entities and order them with attributes. So that's something coming this year. Structs, so composable attributes. When you want to say a coordinate is an X and a Y put together in a bundle, we can't do that yet, so that's something on the roadmap as well. More optionality, partial matches, and conditional writes, so that's happening these weeks. Interestingly, we've had a lot of interest from the agentic AI space, very current. I think that is largely down to the fact that the type system is essentially a form of guardrail. So when people talk about agentic AI doing the wrong thing, or needing some, making sure it's not doing the wrong thing in the longer term, we have people basically using AIs to write TypeQL, and then making sure that it's doing the right thing. If it were SQL, it's harder because you don't have the guardrails of the type system and the type checking. So I think that's why people are coming to us, but also because it looks like natural English, I think it's not hard for people to check things and make sure it's doing the right thing and stuff. And another thing that's our focus for this quarter and next quarter is going to be documentation, accessibility, visibility, quick starts, all of that, because right now the onboarding journey is a little bumpy, I would say, especially documentation. So that's another focus. Yeah, and that's us. So TypeDB is open source. It's the community edition, core edition is fully available. You can read our source. Our language is open source. Believe the language is fully Apache, but the core is Mozilla, something like that. So you can actually play with it. We have a very active Discord community. So
the driver is Apache.
The drivers are Apache as well. We have an active Discord community. Join our server, chat with us, try stuff out. When you break things or if you manage to break things, let us know, because we always value feedback. If you have any opinions, we also are always open to that, because the more we hear from our users, the better it is for us to design the next generation of the roadmap.
Yeah.
And yeah, that's us on GitHub. We have a big org on GitHub with many repos. Go check them out.
Yeah. And there's cloud.
And we have a cloud platform where you can go and deploy instances for free and try it out and not install anything, and it's all managed.
Cool. All right.
Yeah, thank you.
Quick photo of you guys.